Hey everybody, welcome back. In this presentation, we're going to be going over why you should choose Rust for programming. With Rust security, we're safeguarding the future of software. Rust is a modern systems programming language designed for safety, speed, and concurrency. It's increasingly used in various domains like operating systems, embedded systems, and web development where security and performance are paramount. So as an introduction to the Rust programming language, Rust is a compiled language known for its strictness and strong guarantees ensuring memory safety and data integrity. Its focus on ownership and borrowing helps eliminate common memory-related errors, making it a suitable choice for secure software development. So for ownership, Rust's ownership system gives each piece of data a single owner, eliminating dangling pointers and memory leaks. The borrowing system allows temporary access to data owned by others, ensuring data integrity and preventing memory corruption. And static typing, Rust's static type system catches errors in compile time. Rust's static type system catches errors at compile time, ensuring that the data is used correctly and preventing unexpected behavior. Memory safety in Rust. Rust's unique ownership and borrowing system prevents memory-related vulnerabilities like buffer overflows, dangling pointers, and use after free errors. It eliminates the need for garbage collection, resulting in predictable performance and reduced overhead. With ownership, this ensures that each piece of data has a single owner, preventing multiple entities from modifying and accessing it simultaneously. With borrowing, this allows temporary access to data owned by others, ensuring that the original owner retains control and preventing unintended modifications. And with stack allocation, Rust allocates most data on the stack, which is automatically managed and guarantees memory safety without the need for manual memory management. Type safety and error handling. Rust static type system enforces type checking at compile time and eliminating type errors during runtime and ensuring data integrity. Its rich error handling mechanisms allow developers to handle potential errors gracefully. So with strict type checking, Rust's compiler ensures that all data operations are type safe, preventing unexpected errors caused by incorrect data usage. With error handling, Rust provides a robust error handling mechanism through the result type, enabling developers to handle potential errors gracefully and avoid program crashes. Concurrency without data races. Rust ownership and borrowing rules enable safe concurrency. It helps prevent data races and ensures that multiple threads can access and modify data without causing unexpected behavior. Ownership. This ensures that each thread has exclusive ownership of the data it modifies, preventing other threads from accessing it concurrently. Borrowing allows threads to temporarily borrow data from others, ensuring that the original owner retains control and preventing data corruption. Synchronization primitives. Rust provides various synchronization primitives like mutexes and channels, enabling safe and efficient coordination between threads. Ethical considerations in secure software development. Security is not just about technical implementations. Developers should prioritize user privacy, data protection, and responsible disclosure of vulnerabilities. So with privacy, data should be collected, used, and stored responsibly, respecting the user's privacy. With security, developers should prioritize robust security measures to protect the user data and prevent unauthorized access. And for transparency, vulnerabilities should be disclosed responsibly and transparently to enable prompt fixes and protect users. This also helps with the reputation of the developer that makes the software. Security measures and best practices. Following secure development practices is essential for building robust and secure software. These include secure coding practices, vulnerability management, and regular security audits. Input validation. So for input validation, we validate all user input to prevent malicious code injection and buffer overflows. Secure coding. Follow secure coding practices to mitigate common vulnerabilities and prevent malicious attacks. Vulnerability management. Proactively identify and address vulnerabilities in a timely manner to minimize potential security risks. Security audits. Conduct regular security audits to assess the effectiveness of security measures and identify potential weaknesses. Rust code examples: memory safety, null safety, and concurrency. These code examples illustrate Rust's unique features that enhance security and reliability. These demonstrate how Rust handles memory safety, null safety, and concurrency, For memory safety, we have the snippet below. Let mut x equal 5, let y equal ampersand x, and star y equal 10. This error cannot modify a borrowed value. So what's happening here is this line, the first line, let mut x equal 5. This line declares a mutable variable x and initializes with the value 5. The mut keyword allows x to be modified later in the code. Let y equal ampersand x. This line creates an immutable reference y to the variable x. The ampersand x syntax means that y is borrowing x, but y itself is immutable. Since y is an immutable reference, you can read the value of x through y, but you cannot modify x through y. And then star y equals 10. This line attempts to modify the value of x through the reference y. The star operator is used to dereference y, giving access to the value of y points to, which is x. However, since y is an immutable reference to x, Rust's borrowing rules prevent you from modifying x through y. Rust enforces strict rules to ensure memory safety, and part of that involves distinguishing between mutable and immutable references. An immutable reference does not allow you to change the value it points to. So the error occurs because you're trying to modify the value of x through an immutable reference y. Rust does not allow this because it would violate the guarantees that immutable references provide, that the value that they point to won't change. So to correct that value, if you want to modify x through a reference, you would need to create a mutable reference instead. And that would be let mut x equal 5, then let y equal ampersand mut x, and then star y equal 10. And in this corrected version, the let y equal ampersand mut x creates a mutable reference to x, and then star y equal 10. This is allowed because y is a mutable reference, so you can modify its value that it points to. So for the null safety example, let x option equal sum 10 in parentheses, let y equal x dot unwrap underscore or 0 in parentheses. No null pointer exceptions. So in this example, let x option equal sum 10 in parentheses. This line declares a variable x of some type option. The option type in Rust is used to represent a value that can either be sum, holding a value, or none, representing an absence of a value. So sum 10 is used to indicate that x has a value of 10 wrapped inside of the option type. Now, when I was doing some research on this, it would pop up in I32, which is, it specifies the type of value inside the option, which is a 32-bit integer. For the next line, let y equal x dot unwrap underscore or 0 in parentheses. This line calls for the unwrap underscore or method on the option variable x. The unwrap or method is used to safely extract the value inside an option without causing a program crash. If the option contains some value in parentheses, unwrap or returns that value. If the option is none, it returns the default value provided as an argument to unwrap or. In this case, x contains sum 10 in parentheses, so unwrap or 0 in parentheses returns 10, and y is assigned the value of 10. If x were none, unwrap or 0 in parentheses would have returned 0, and y would have been assigned 0. And then the comment, no null pointer exceptions, the comment refers to Rust safety features. In many other programming languages, attempting to access a value from the null reference none in Rust could cause a runtime error known as a null pointer exception. Rust option type avoids this issue entirely by making it impossible to accidentally dereference a none value. Instead, the methods like unwrap or provide safe ways to handle the optional values. And for the concurrency example, I won't read the whole thing, you can read it in front of you, but I'll do a step-by-step explanation walking through it. So in the first line, use standard sync MPSC. This line imports the MPSC module from Rust standard library. The MPSC module provides functionality for message passing between threads. The acronym stands for multi-producer single consumer, meaning multiple threads can send messages, but only one thread can receive them. In the next line, let tx, rx equal MPSC, and then channel with parentheses. Here a new channel is created using MPSC channel parentheses, which returns a tuple containing two parts, a transmitter TX and a receiver RX. TX is used by the sending threads to send messages into the channel. RX is used by the receiving threads to receive messages from the channel. So in the next line, TX send 10 dot unwrap parentheses. This line sends a message, in this case the integer 10, into the channel using the TX transmitter. The send method returns a result which can either be OK with two sets of parentheses if the message was sent successfully, or an error, ERR, if there's a problem, for example, the receiver has been dropped. And finally, the unwrap method is called on the result to panic terminate the program if there's an error. In this case, it's used to ensure that the send operation succeeds. If it doesn't, then the program will panic or terminate. And then finally, let received equal rx dot receive, or recv parentheses dot unwrap parentheses. This line waits to receive a message from the channel using the RX receiver. The recv method is blocking, meaning it will wait until the message is available on the channel before returning it. It also returns a result, which can then be OK, and then T in parentheses, where T is the received message or error, ERR, if the channel is closed and no more messages will be received. Unwrap parentheses is used again to panic or terminate if there's an error, ensuring that the received gets the message 10. So to go over the comment, safe and efficient thread communication, the comment refers to how Rust MPSC channel provides a safe and efficient way for a way to communicate between threads. Safe, Rust ownership of the system. Safe, Rust ownership system ensures that the data sent through the channel is transferred safely, preventing data races and other concurrent issues. Efficient, channels are a low overhead way to pass data between threads, making them a suitable tool for many concurrent programming scenarios. So in conclusion, Rust offers a compelling solution for modern secure software development. Its unique features like ownership, borrowing, and type safety ensure memory safety, prevent data races, and enable efficient concurrency, ultimately contributing to safer and more reliable software. So I'd also like to showcase my website that I put together for this final project. So the slide deck and the website go hand in hand. In the website, I called it Rust Guard, and it's basically exploring security and Rust programming. So a lot of the material that we covered in the slide deck is covered within the web page. So the first page is just your typical home page, and I scroll down here and kind of go through getting started with Rust in the real world, showing some different examples. And then on the About page, we go into the Rust revolution, a new era of secure programming. And then we go into talking about memory safety, concurrency, zero cost abstractions. It's a growing ecosystem. It's a pretty short page. And then we go into the ethical considerations. So we talk about the responsibility in code quality, accessibility and inclusivity, transparency and trust, and then the resource allocations. And then for the security measures, we want to fortify our code. And Rust has a very robust security arsenal. So we talk about memory safety, type safety, safe concurrency, secure coding practices, and then third-party security tools. And then finally, for resources, if you want to dive deeper into the Rust security resources that are available out there, there's a few examples of different books. The Rust programming language, Programming Rust, and Rust for Rustaceans by these various authors. There's some different online courses that are both on, one's on GitHub and the other one's on doc.rustlang.org. And there's some tools and libraries on GitHub, and then some community resources for the rust-lang.org, and this week in Rust with hyphens in between .org. So these are all powerful resources available in case you want to take a look deeper into what Rust has to offer. So that's about it. If you liked this presentation, please hit the thumbs up and leave a comment below, especially if you have any questions. I'd be happy to answer them for you, and I will see you all next time.